We will continue our discussions of building blocks. In our last video, we built three building blocks. One is a uniform flow, the other one is source, the third is a sink. Then by snapping them together, we were able to get some interesting flows, such as a flow over an oval-shaped body, which is called Rankine's full body. Notice that these lines are streamlines. They flow around the body, so they automatically satisfy the tangency condition. In fact, the body shape is psi equal to 0. So all along the line, psi equal to 0, which is a constant. Along a streamline, stream function psi is constant. So psi equal to 0 line starts from far upstream, comes this way, split it into two halves. One goes over the upper side, other one goes over the lower side. When it reaches here, it continues as psi equal to 0. So this is the body. Now we look at the next building block, which is called a doublet. A doublet is simply a source-sink pair that's separated by a distance delta. So we let delta go to 0, but we don't want the source to eat up the sink, disappear. Neither one will be around. So we increase the strength of Q as delta is decreased. So source is placed at point A, sink is made at point B. Q times delta approaches a constant, which we call mu. Not a viscosity. This happens to be the symbol mu in many books. This is called the strength of the doublet. So remember, Q is like a volumetric flow rate. This is times the distance. So it's got an extra distance to it. So the question is, what would be the stream function at point A? We're going to place source A at the origin. So we're computing the stream function at a point called P. So this the angle is theta. Sink is here, so this angle is theta. So what is the stream function used to the source and sink? Two Lego pieces side by side placed. And this is the distance delta. We're going to let delta go to 0 in a minute. Now, psi is Q over 2 pi times theta, which is this one. That's the source. Q over 2 pi times theta plus delta theta is the sink. So if you subtract, one is positive, source, other one is negative. So when you do that, you'll just get Q over 2 pi times delta theta with the minus sign. Okay. Now, we have to get an expression for this delta theta. Okay. So we do a little bit of trigonometry. So this is the line B. So we call it this line BP. Okay. This distance is R. Okay. And this subtended angle is delta theta. Okay. Because this is theta plus delta theta, therefore the subtended angle is delta theta. So in the limit as delta theta goes to 0, EP will become pretty much same distance as R, because this point will approach this point. Okay. Therefore, we could say that the EP, which is R times cosine of delta theta, equal to just R, roughly. So this is R. Okay. Now, AB is delta. Therefore, EB is delta. This is the hypotenuse. This is theta, delta times sine theta. Okay. So this is delta times sine theta. This is R. Therefore, this would be R times sine of delta theta, which is just delta theta, which is R delta theta. So equate this expression for EB, which is R times delta theta, with this expression EB equal to delta times sine theta. Then we can get an expression for delta theta equal to delta sine theta over R. So plug this delta theta in here, then you get an expression for psi of a doublet. Now, this has got a Q here. We pick up a delta from here, q times delta, as the distance delta goes to 0, q times delta approaches mu. Therefore, we get minus mu over 2 pi. The 2 pi is from here. Sine theta over r just carries on here. So this is the stream function for a doublet, a source sink pair. Source strength is mu, sink strength is minus q, string strength is minus q. Delta is the distance separating them, but we let delta go to 0 and q times delta approach this constant, which is mu. Now we can look at the flow over a body. It turns out to be a circular cylinder. So again, we take a uniform free stream in the x direction only. So the psi due to the free stream is u infinity times y. This is the doublet solution that we just derived up here with the minus sign in front of it. This is in Cartesian system, this is in polar system, so we need to go to one system or the other. So we put y equal to r sine theta from the polar coordinates. Then you get u infinity r sine theta minus mu over 2 pi sine theta over r. Now, sine theta is common to both terms, so I can take it outside. So I'm going to take an r sine theta outside, and I'm also going to take u infinity outside. Then you get 1 minus mu over 2 pi. I pick up an extra u infinity because there's an u infinity here. Then since I have a 1 over r, whereas there's a r here, this becomes 1 over r squared. Now this is a positive number because free stream is positive. Source times distance, q times delta is a positive, so this is a positive number. So depending on the source strength, q times delta, you'll get a bigger number or a smaller number, depending on the magnitude of u infinity. If u infinity increases, you'll get a smaller number. If u infinity decreases, you'll get a bigger number. In any case, this is a constant. So instead of having one constant here, another constant here, we can lump them together into a new constant, which we call r squared, positive number. Then you get an expression for stream function like this. If you now examine this stream function, we can contour plot it in MATLAB, but before that, let's do some very simple examination. We notice that when theta is 0, psi equal to 0. That means along the x-axis, especially downstream of the body, streamline goes along the x-axis. When theta equal to pi, psi is 0. That means upstream of the body, again along the x-axis, psi is 0. Thirdly, when r equal to capital R, that means around a circular cylinder, psi goes to 0. Therefore, psi is 0 if r equal to r, or if theta equal to 0, or theta equal to pi. So if you draw the geometry, that's going to be a circular cylinder, x-axis in front of it, x-axis behind it. So we have drawn the streamline that comes towards a cylinder, breaks it in two parts. One goes over the upper surface, one goes over the lower surface, then rejoin at the back end, then go along the x-axis. Let's take a velocities. Vr this is the derivative definition of velocity. We can take a derivative of d psi d theta, which will be cosine theta. 1 over r, therefore this r will go away. Then you'll get this expression. So on the body surface, when r equal to capital R, we get a 0 normal velocity. That means the flow is tangent to the circle. Therefore the circle itself is a streamline. So if you plot it, psi equal to 0 will start here along the x-axis, come all the way here. Psi equal to 0 will go over the upper surface. Then psi equal to 0 will go over the lower surface. Same way, psi equal to 0 will start here, go over the lower surface, and downstream this way. Remaining streamlines, all the positive psi will be above, all the negative values of psi will be below. Okay? So this is the streamlines that we saw earlier. Notice that it's a symmetric front and back. Therefore, we don't expect any velocity differences because velocity differences are proportional to the area. This area is same as this area, for example. You get a stagnation point here. you get a stagnation point here. Therefore, it's symmetric, no drag, of course, no lift. In real world, of course, we have viscous flow. So behind the body, we get a separated flow, so we get a pressure drag. On the body, boundary layer scrapes past the surface, so producing a skin friction or a frictional drag called a skin friction drag. So we do have a drag in real world. So this is flow singularity called doublet, and we have taken a doublet and a free stream velocity, and we have come up with flow over a cylinder. So we are going to stop at this point.